Ah, can you hear me now? Uh, Today I will present first two part, and then I think Sam will come today, and then we will have time for your class project. Yeah, I will start presentation maybe in 3 minutes. Oh, by the way, how do you present your? Yeah, I guess we usually yeah, I'm not exactly sure. Okay, good afternoon. My name is Seonghyeon Moon, and I'm also under Professor Mubasir Kapadia, and I'm also these two part is my recent project. So I would like to share my work, and the second part actually I will just introduce the current related works. What about fusion segmentation? So I think each part will just take 20 to 30 minutes. So yeah. So the first part, the title is an integrated platform for joint simulation of occupant building interactions. My presentation will follow this order. I will briefly introduce the problem first and show other approach to handle how to handle this problem. After that, I will explain our approach, result, and conclusion. This work is about the simulation work. So maybe if you're not interested in this work, but it will be good for you. It's like, what is the simulation? So in the modern world, handling data is getting more attention and getting more popular than before. And this trend has been affecting building design aspect as well. Nowadays, there are many building simulators have been developed and keep evolved. Recent building design is using building information modeling so that architects can design building more efficiently and easily. However, still simulating occupant building interactions has been remain challenging work. How real human interact with the building is still questionable. If architects design a building without considering people who are going to stay in a building, these kind of problems could be occurred during design stage or later in building maintenance. Lack of productivity, burnout, energy imbalance, dissatisfaction, inefficiency, and loss of money. Here are two simulations. The left side shows the building energy simulation, and the right side, crowd simulation. The one left building energy simulation provides mainly energy cost for building, but it's not representing occupant movement. But the crowd simulation, it represents low-level occupant movement, but it ignores high-level action that may affect energy cost. So both are great tools for each core, but none of them are for occupant building interactions. To solve this previous issue, lack of information of building occupant interaction, we proposed scalable and practical way to combine these two different simulators into one building occupant interactions. So in other words, we are going to make integration platform join, which is enabling the joint simulation of building occupant simulation more scalable and practical way. So our proposed platform join will show how joint simulation of occupant building interaction can be implemented. There are two ways to integrate of two simulators. The one is co-simulation which runs in parallel and exchanging information. But this one, it often requires the modification of existing simulators to send and receive information and be controlled to be controlled by another program. And the other approach is model independent simulator, but it requires developer to understand the common set of modeling convention. This table shows all the other approaches, how to join this kind of two different simulators. Each approach has own merit and demerit. Compared to others, our approach here, the join, our approach method uses steps convention with unrestricted event times. It combines crowd simulation, planning, footstep, noise, and heat in a unique platform. Yeah. The proposed prototype join is extensive and multi-purpose platform that support joint modeling and simulation of mutual interaction between building phenomena and occupant behavior. And these are four key features of our proposed method: joint modeling of domain phenomena, multi-level decision-making, multi-time scaling, multi-time scale modeling, and multimodal representation. Our work utilized the framework called SciDeps, and we established steering simulator named SteerSeat. We used the steering simulator named SteerSeat as well. So this way, it makes the model independent approach to be more flexible to combine other simulators. Here, the SciDep is symmetric discrete event system specification, which was proposed by Goldstein in 2018. This is for general purpose modeling frame. So it utilized node system to for designing simulation work. So SciDeps provides common interface, allowing different simulators to be combined and coordinated by single model independent framework. Using SciDeps simulation code is very well organized into node system, which can be linked together to form data flow and simulation networks. Here, each block is node, and each block is linked by these arrows. And this slide showing general approaches of SciDeps. Left side are for initialization for the data. And in this stage, we set high parameter or parameter for and we do some simple calculation before going to simulation stage. And middle nodes take previous parameters and do simulation task and pass result to the right side finalization node. So in the SciDep, there are two nodes, function node and atomic node. The function node represents a single function that reads a set of input values and calculate a set of output values. And the atomic node provides general structure for representing behavior that unfolds over simulated time. And there is one more node called composite node. This node integrates the previous two nodes, and they can link using their port, like here anyway, there are initialization and finalization links which form a data flow programming graph. There are also simulation link which direct message and support discrete event simulator. So, and inside the node, there are 4 events to control the order simulation. The initialization events only invoke before any other event handling function. An unplanned event is only invoked every time when this node receives message. And planned event function is invoked whenever the planned duration elapsed. And finalization event only invoked after all the events are finished. All this work implemented in modern C++. And the other simulation work called SteerSuite, which is framework for modeling occupant movement. This one was proposed by professor, Mubassir Kapadia, in 2014. He did this work, I think, when he was in PhD student. Yeah, and there we utilize these two models, social force model and footsteps model. The social force model compute agent speed and direction. The social force model compute agent speed and direction using the sum of attractive and repulsive force here. And there is another, the other one is footstep model, which simulate biped movement using biomechanically inspired approach. This figure shows that how the previous steer suite works. So first, we need the target information. So first, we need the target information for the long-term planning, and using this long-term planning, we again find another. We find a mid-term planning again, and then using the mid-term plan again, we find the short-term planning. This core information and reaction information are considered to take the next step in the locomotion function. Yeah. So we have two simulators, SIDEPS and steer suite. SIDEPS supports high-level planning and steer suite support the low-level steering. And SIDEPS use discrete event system and steer suite use discrete time system. So thanks to SIDEPS flexibility, we can add different models to our framework, even heat simulation and noise simulation. And our proposed platform join support high-level planning and lower-level steering because we integrated two different simulators. Also, our platform support discrete event and discrete time. And also our model can use this social force AI and footstep AI model. This slide represents our prototype join overall structure. We use the SIDEPS nodes to add the steer suite framework. This left yellow node shows the initialization node. So as I said before, this initialization node set the initial parameter and do some initial calculation before doing the simulation task. And this right side block shows the simulation node. So all the simulation task is done by the right side. Yeah, and the nodes in the red box are from steer suite functions and produce all agent locations. Thanks to this kind of node representation, we can add acoustic and heat simulation as well. Compared to the previous slide, you can see there is the 3 more additional nodes. So this way we can add more simulation easily. Yeah. And this simple video clip shows that how the heat and the temperature in the building is spread in a building. So all the people are going to their destination, conference room or their desk. So this figure shows different simulation snapshot. The figure A shows at the beginning of the video clip, and Figure B shows the temperature heat map, increased indoor temperature in the meeting room, especially. And snapshot C shows that because we put some threshold for the people, so when the temperature in the room over the threshold, then people are escaping this conference room. So you can see that. Oh, in this simulation, main heat source is from the human, so all the heat is from the human body. And also we analyze this or the trajectory map like this. So we found that where the dense area, so in this case, A and B utilize different AI model. So when we used this social force model, we can see that this the congested area is like a very narrow area, but for the footstep model, we can see that the more agents are using open space more than the social force. The social force model produces congestion in this proximity to the building entrance, while the footsteps congestion is in the lobby. Yeah. Okay, I think we can skip this part. And we tested this noise simulation as well. In this model, we simulated that whenever agent make a step, we believe there is noise. So using that kind of noise, and then we calculate how the noise can be spread to in building. Yeah. So yeah, it's the same for before. We take a snapshot for the previous video, and yeah, that's her. And we analyzed the impact of the floor. If the floor is sound absorbing, then you can see that the noise is decreased. Yeah, this one also show that how each agent is impacted by this temperature and sound. And we found that this table shows that our joint platform in computationally there is no negligible computation time for this kind of work. So for the conclusion, Join is an extensive and multi-purpose platform for simulating building occupant interaction that span across multiple levels, domains, timescales, and models. Join support the communication between servers with the negligible computational overhead. Thus, removing technological barriers associated with combining different models into an integrated system. Furthermore, it combines a wide range of simulators, including high-level occupant planning, low-level occupant movement, heat and sound in an integrated framework. Yeah, that's all for the part one. Yeah. Do you have any question? No? Oh, yeah. The second topic is recent advances in future segmentation. Maybe, can we start maybe 5 minutes later? Okay, the second part is recent advances in few-shot segmentation. I will introduce few-shot segmentation about the few-shot segmentation. So this will be very short, just introduction about what's the few-shot segmentation and the currently related work. In computer vision, there are four tasks, very most classic tasks. One is classification, and second is object detection, image segmentation, and visual relationship. Here, the object classification is when you given the image, you need to classify what's the target object. And for the object detection, you need to find the bounding box for the target object, not only the classification. And for the image segmentation, it goes further. You need to find very accurate location by pixel by pixel. There are two segmentation, actually, the semantic segmentation and instance segmentation. In instance segmentation, you need to differentiate even in the same class. So it look like a right figure, you need to find the SHIP1, SHIP2, SHIP3. So again, segmenting is finding class from the given image, input image. We can classify the classes using this kind of pixel values. In 2012, AlexNet was introduced, and it showed good performance in object detection and object classification tasks. And later, 2014, VGG16 was introduced, and they used the more pooling layer, and then it shows better performance than AlexNet. After VGG, the ResNet introduced, and this residual network still utilized in many forms, even in transformer network. In 2014, this paper, fully convolutional network for semantic segmentation, is introduced. And I believe that this is the first paper they started doing this segmentation work. So that time, they deleted the fully connected layer. Instead, they used fully convolutional network. After the previous work, this kind of encoder-decoder structure becomes very popular for the segmentation work. Because when the fully connected layer is attached, spatial information is disappeared. And also, if there is no downsampling, then parameter size is too huge to do this task. So they find some middle point by using this downsampling and upscaling. In 2015, UNET improved the encoder-decoder structure by using this cyclic connection. So for the decoder part, this previous encoder feature is added, so they can maintain the previous feature vectors. In 2016, Segnet introduced, and in their case, they use the pooling indices, and the indices for the pooling are passed to the decoder part for the upsampling. Yeah, so far we studied the history of segmentation, supervised segmentation work. In supervised learning, we train and then test samples which are never seen before. So in this slide shows that the Husky class is in the training set. And then we test Husky class again. for the testing our model. But this kind of supervised learning requires large amount of annotate images for training. And once the model is trained, it cannot be generalized to unseen categories of object. But in future learning, we record query sample, but yeah, it's the same as test sample before. The query sample are never seen before, and query samples are from unknown classes. So during training stage, our model doesn't have rabbit here. But we will ask a model, what's this rabbit image? Then we have a question, how AI can predict this rabbit image is rabbit? In future learning, we have another image for helping the model. We call support set. In this case, we have 6 classes. So we call 6 way. And because there is one sample for each class, so we call one shot. So in this task, we call 6 way one shot object classification. So here is the one task, 6 way one shot object classification. We call just one shot classification, object classification. Using the support set, a network can find the closest animal, and it can predict correct animals. Now let's look few-shot segmentation work. In few-shot segmentation, you have support image and support mask. And this support set helps the model to guide which target object should be segmented. In this slide, the network should segment this elephant. Yeah. In one-shot segmentation, there is one support set like this. In this figure, support set shows that which target object should be segmented. In this case, the human should be segmented, but the network failed to predict the human here. This case, 5-shot segmentation work. And now we have 5 examples, 5 example support set. And now the network understands what object should be segmented. Yeah, comparing ground truth, you can see that prediction is quite good. This kind of way doing segmentation is actually pretty new task. It's believed that Schabenetter introduced this task in 2018 first, and now this task becomes quite popular. So what they did first is quite simple at that time. They first use the support set. They feed this support image to the VGG network and get the parameter for the C function. And then later, this query image, and also they get the query feature from this query image. And then this query feature goes to C function together, and then later make the mask prediction. Yeah, it was very simple way to do that. And there are many diverse approaches, but we can say that there are 3 typical way to do this few-shot segmentation task. So first one is same as before. We need to get feature vector from the support set and then find some cosine similarity between support feature and Corey feature. And the middle figure shows that using the cluster approach to find the closest object. And the last one, someone tried the graph attention network to find the closest feature vectors between this support and Corey features. Oh, by the way, the first one is, oh yeah, I will skip. And today, lastly, I will explain the very recent work. This one shows the best performance in few-shot segmentation. And this paper just published 4 or 5 months ago. And this title is Hypercorrelation Skis for Few-shot Segmentation by Min et al. 2021. This slide shows the overall structure of the network. Yeah, it looks very complex, but if you look in detail, you can understand it's not actually difficult. So they have 3 core parts: hypercorrelation construction, 4D convolution pyramid encoder, 2D convolution decoder. So simply we can say that it has just encoder and decoder. And the first part is just generating feature vectors. So first, they generate feature vectors instead of using the last layer of the backbone, because the previous work only used the last layer to get the feature vector, but instead they utilize her feature vectors from every layer, and they stack all the feature vectors. So you can see that all the block, like they constructed this kind of block for the every layer. Yeah, this way they say that they maximized getting all the feature information. And these feature maps are constructed into 4D vectors, and they introduced this 4D convolution network to squeeze these feature vectors to some fixed channel. Like here we use, the paper used the 128 channels. So this part is encoder. Now we are looking the decoder part. So decoder part is just use the previous keys vectors for the decoder stage. So here the paper just used upsampling and simple addition, and then they again upsample again to match the input image size, and then they get the prediction mask. And yeah, that's all about this work. Yeah, you just figure out how the best fusion segmentation is working. So yeah, that's all for today. My part, and we can start the part 3. Thank you for listening, by the way. Yeah. Do you have any questions? Oh, Sam? Okay. Wait. Are people on the Zoom call? We are two. Okay. Okay. Are you sharing your screen? Yes, this screen. What about your webcam? This for the just mic. Oh, I see. You're not showing your face. Okay. I don't really know how helpful it would be. I think we can start with the people on Zoom for their updates. Okay. Sure. And then, because then at that point, I think everything is rather like individualized, so we can just shut up the Zoom call. Yes. Oh, by the way, hi everyone. I was here like, I don't know, 2 months ago maybe. I was asked to come back to help with the project update part. I don't know why he chose me, but you know. Yeah. Wait, do you have your volume on, right? Oh yeah, yeah. The people in the Zoom call right now, do you have partners in class right now or vice versa? If anyone here knows. So on Zoom, there's Harsh Patel, Karthik Chava, and Sangwoo An. Is anyone in here also in a group with them? Because who are you in a group with? Harsh Patel. Okay, and for the other two people, no one's in a group with them? Okay. Karthik and Sangwoo. Oh, I see. Okay. Do you guys want to give an update on your progress so far via the Zoom, and then we can just end the Zoom call there, and then you guys can, you know, go at your day. Is that okay with Karthik and Sangwoo? Can you hear me? Okay. Oh, he just left. Okay. Karthik, are you there? All right, I'll assume they're not here. I think it's fine to end the Zoom call because we're not getting a response from Karthik. And Harsh can follow up with his partners in class. Yeah. Okay. I went through some of the, well, actually, I skimmed through most of the project updates for Discord, and it seems like at least at this point, everyone that's doing machine learning is finishing up